This webinar contains information, some of which you already know very well from daily routine, but some of which may be a new information for you, I hope. We will talk about neurography, both motor and sensory. These are very useful techniques, and they are mainly used to detect polyneuropathy and local neuropathies, focal disorders. And we try to tell about the pathophysiology, severity, and distribution, including the localization. The methods that we use are standard motor neurography, and I consider F-wave studies being as an integrated part of the motor neurography. It's not a separate study. Then standard sensory neurography with surface electrodes, and then very uncommonly near nerve electrodes, and then short segment studies, earlier called inching technique, that we particularly use for the study of slowing of conduction at the elbow and across the fibula head. I have many pictures on electrode placements that we use in our lab, and that can be seen in a handout that I will provide shortly. Just one picture showing that we use surface electrodes that can be glue-on electrodes like this, and we place one over the belly of the muscle, and the other is not over the tendon, which is here, but further away, and we use to place that electrode at the most distal interdigital joint, both in hands and in feet, in order to get that electrode as silent as possible, not picking up activity from the muscle under study. And then we have surface electrodes for recording, and we have standard distances between the stimulator and the recording electrode. And what do we learn from neurography? Well, you all know this, but I just take a short look at it. Here is to the right the muscle, and we have distal stimulation and obtain a signal, and we have a proximal stimulation and obtain a signal. And in this way, by subtracting the two and measuring this distance, we can obtain conduction velocity. So what we record is amplitude, which is related to number of axons, the neuromuscular transmission. In myasthenia we have lower amplitudes, and the muscle volume. And the conduction velocity is related to the state of the myelin, and also dependent on axonal diameter. The measurements are usually including parameters such as distal latency, which is indicated at the first takeoff of the baseline, or some other point that I will show. The amplitude is measured between baseline and negative peak. The duration is measured between onset of the signal and the first zero crossing line, and then the area is the segment under the negative part of the signal, and the difference in conduction times are called conduction, and this is the conduction time. I will show a few examples of things that we can obtain with neurography. The first one is conduction block that happens in demyelinating disorders and also in focal lesions, and they are important to recognize. Conduction block is that when we stimulate distally, we may get a completely normal signal, but when we stimulate proximal to the area of pathology, then not all signals are passing, and therefore amplitude is lower. And the difference in these signals is expressed in percentage and is called amplitude decay. Here is an example of Guillain Barré, where we have the distal stimulation with a good amplitude of 3.7 and a proximal amplitude of 1.1, and it's a 70% difference. Somewhat slow conduction velocity, and importantly no F waves, or just one F wave. If we have something we think is conduction block, then we cannot have normal number of F waves, so that is an important quality control. And the criteria for conduction block is studied in many publications, and there are a lot of suggestions and definitions. We have used a combination of the different definitions and say that if amplitude is decreasing by more than 25% at the same time as the signal is more or less unchanged in its duration. You know, if we have an increased duration, the amplitude also becomes smaller. So a dispersion, change in duration, should be less than 15%. And for the leg nerves, we have the fibular nerve. If we have an amplitude drop of more than 30% and less than 30% dispersion. And the tibial nerve, we allow up to 55% amplitude drop, and the dispersion should be less than 45%. This high amplitude drop is due to special conduction conditions among the small foot muscles, so it is not really inexcitability or any conduction block along the nerve. And in addition to this drop in amplitude, we also have reduced number of F waves. We can say that conduction block really is associated with weakness. No impulses are passing. If we have just a temporal dispersion, that is not giving weakness. We can easily wait for a few milliseconds for an impulse to pass. And block is important to detect and report. That is often an autoimmune neuropathy, may be treatable. Then we have demyelination situation. Depending on where that happens, we may have a completely normal distal latency, but when we stimulate proximal to the problem, that can be either focal or more generalized, we have a longer conduction time there, and therefore this comes later, and often the signal is slightly more dispersed than at the distal stimulation. The amplitude is often just changed very little, and here's a typical example from a patient with Charcot-Marie tooth type 1. We have distal stimulation here with a prolonged distal latency, and here is the proximal and conduction velocity of 35 meters per second. Amplitude more or less normal for the median nerve here, 5.2 millivolt, and no amplitude drop. It is the amplitude dropped 16% and the duration increased only by 6%. There are different definitions of demyelination. It's difficult to say an absolute condition where we have or not have demyelination, but the rule of thumb is that conduction velocity is reduced to less than 60% of mean velocity, and that means for example less than 38 meters in the median nerve in adult, and the prolonged distal latency more than 7 milliseconds, and normal or slightly reduced amplitude. That is the hallmark of demyelination. Now we go to the other type of pathophysiology, axonal degeneration. Distal latency is completely normal, but the amplitude is low because we have fewer axons that are activated. And the proximal stimulation activates all these axons, but many of them have become degenerated here, and we have a Wallerian degeneration, so they are not active here, and therefore we stimulate only those that are surviving, and therefore recorded with an amplitude very similar to the one we get at distal stimulation. So low amplitude, more or less normal conduction velocity. The velocity in median motor nerve more than 40 meters is said in many publications. Distal latency normal or slightly prolonged, and no amplitude decay. Well, that seems to be easy, that differentiation between demyelinating and axonal neuropathies. We have demyelination with slowing of conduction velocity, and the amplitude on x-axis is within normal limits. Whereas if we have an axonal polyneuropathy, then we have low amplitude and more or less normal velocity. And the problem we have in our daily work is in this area, where we have little of demyelination and little of axonal changes. And that is first of all true biologically, that axon and myelin are dependent on each other, so we have real combinations. And when we try to choose here, we have to go for the most dominating criterion. If we have very much of slowing, or if we have very much of reduction in amplitude. I should say that 85% of neuropathies are of axonal type. Here is some examples of conduction velocity in the normal. We have distal stimulation, more proximal and even more proximal here in the fibular nerve. And here we have a patient with CIDP, where we stimulate distally, and we have some late components. These are very low amplitude, difficult to see. When we stimulate a little more proximally below the level of the fibula head, we see these late components giving a dispersed signal, and that is even further if we go more proximal. Charcot-Marie-Tooth is a very homogeneous slowing in all the axons, and therefore the signal is not dispersed, but just all of the signals are delayed, slowing in conduction velocity. Here it was 27 meters per second. And here we have an ulnar entrapment, where we have distal stimulation. We have a relatively good signal just below the sulcus ulnaris, but above sulcus ulnaris the signal is dispersed, and it's more notchy than this one signal. So one can judge a lot about the shape of the signal from different stimulating points about the pathophysiology. Now we shall discuss the neurography and the difficulties and pitfalls and the influential parameters. We have many technical parts that can play a role: electrode type, position of the electrode, reference electrode, muscle length, and so on, temperature. And we have the biological parameters that we are really interested in, namely number of axons, size of motor unit, neuromuscular transmission, axonal diameter, and myelination. So let's go over examples of that. The electrode type, they are not symmetric, all the electrodes. They can be elongated in different ways, and larger electrodes give lower amplitudes than small electrodes. Here is one that you glue on, and this happens to give an amplitude of about 10 milliamp. Here's another electrode that is elongated here, and that means that it makes a difference if we have the electrode along or across the muscle. If we have it across the muscle, we get shorter signals and we get higher amplitudes. Here it goes from 10 millivolt to 12.3. And here is a rounded electrode that is independent on the rotation, and that gives, in this case, 10.4 millivolt. Well, there is no truth. You can use any of these electrodes, but the reference values that you use must be obtained with exactly the same electrode. Otherwise, you get erroneous interpretation. Here's another thing that we may not think of so much. The position of the so-called E1 electrode and the reference so-called E2 electrode. Long ago it was recommended to have the belly tendon position of the electrodes, but that is no good. We have the reference further out to the distal joint. I'm interested to see what is the real contribution to the E1 and what is the real contribution to the E2, and therefore we record from the muscle to a remote reference that is not stimulated at all. And here we record from the reference to a remote control point here, and let us see the signals. Here is the conventional subtraction signals that we obtain, and here is the pure muscle signal, that is fine, and here is the reference electrode signal. That is very fine. It's not much active at all, and this minus this one will give this response. If we do the proximal stimulation to the median nerve, then we obtain this signal that you recognize. But if we just record purely from the APB, then we get an early phase here on the signal, an identical phase for the E1 and E2. This is the action from forearm flexors that we stimulate with proximal stimulation, and this signal and this is identical, you see here, and they are subtracted and you don't see them at all as a problem. The same thinking for the ulnar stimulation, ADM and little finger, and we test that in this way, and here we see the typical 2-spike signal, and we have the pure recording from the ADM here, and we have a recording from the little finger, an upside down signal that is coming from the activated ulnar innervated interossi muscles that will remotely give this volume conducted signal. When we stimulate proximally, then we will get the small extra signal from flexor muscles, but not very much at all, and this remains because this is generated in the hand and not in the arm. Here is something rather fantastic in the tibial nerve, where we record from, we say, abductor hallucis, and here you see the conventional standard recording, abductor hallucis minus big toe. We have the E2 over big toe. If we just see the contribution to big toe versus a remote reference, you see a very large signal that is recorded from the so-called reference. And this is obtained from the many small muscles in the foot. This is the abductor hallucis response, very small, much smaller than the one to the reference. And when we take this minus this, we obtain this signal. So the main part here is really coming from the reference, and it really doesn't matter so much if we place this electrode exactly on the right spot. When we do the same thing with proximal stimulation, we usually obtain a smaller signal that is normal, and when we stimulate at the fossa poplitea and record from the big toe, you see that small response, but we also have an early response here, and this is coming from the tibial innervated leg muscles. Exactly the same when we record from the abductor hallucis, and when we subtract them they disappear, and we see this response. So the abductor hallucis is a very small response here. That was the effect of reference electrode. Now we shall look at some other things. Effect of muscle length. If we passively move the thumb backwards and make the muscle shorter without activity from the subject, we see that with stretched muscle we get this amplitude 7.1, and then we make a passive flexion so that the muscle becomes shorter. The amplitude goes to 8.5, 9.5, 10.6, 12.2. You see a very large change in shape with shortening and also with higher amplitude. This has, for example, importance when we do repetitive nerve stimulation, and particularly when we do high frequency stimulation. The muscle is shortened, and part of the so-called facilitation is pseudo-facilitation because of muscle shortening. Another thing that is important is the effect of distance between stimulator and recording electrodes. Here is the motor side. 8 centimeters was used here, and we get this signal. And when we go to a proximal position 22 centimeters, we get a somewhat lower amplitude, but not very much, and we go even 8 centimeters further proximal, then the shape may change a little. In contrast, when we do the same thing with the sensory, the 14 centimeter distance, which is standard for us, we get high, good, nice signals. 22 centimeters difference in stimulation recording position, you see a much lower amplitude with a reduction of 49%, and if we go a little more proximally, it is even a lower amplitude. So these short sensory axon signals, they will decay in amplitude much faster, much more dependent on distance than the motor, and therefore it's very important that our standard for sensory recordings is really very strict on distance. Well, the daily problem with stimulus artifact we all know. Depending on the conditions in the room and in the skin and all these things, we can get sometimes very large influence from the stimulating pulse, and that gives erroneous recordings of amplitude and latency. So here we must try to get a flat baseline, and one way is to move the ground electrode between the stimulating and recording electrode. Another is to rotate the stimulator around the cathode so that the cathode is constant position and the anode is moving. And another thing that I don't show the signal is to use biphasic pulse stimulation, which is available in many EMG equipment. Now we shall look at another thing which is very good at the ulnar evaluation. That is to stimulate with short distances. Earlier this was made with 1 inch between the points. We have used 1 centimeter, and labs use different techniques. So therefore we call it short segment study. We have 3 or 4 points below the sulcus ulnaris and 4 points above the sulcus ulnaris, proximal to the sulcus ulnaris. And here you see the normal situation with a forearm stimulation, good recording amplitude, and then with longer and longer distances we get a harmonic increase in latency. A very small jump here just over the sulcus ulnaris is typical. If we now have a problem in the sulcus ulnaris, it may look like this. A good forearm recording, and here increasing latency, and all of a sudden a jump. And then it goes on with the same latency increase as we have in the forearm or at the distal parts of the study. And that means that this is a true jump here at one place and not an artifact. So here is a demyelination that gives us a local slowing. Good amplitudes and no amplitude change, no amplitude drop. Here is a recording from a patient with foot drop, and we record around the fibula head. Here is a recording at the wrist. Here is a recording at the ankle, and here we obtain the responses from below the fibula head, and here is above the fibula head, and you see that there is a sudden jump here, which is demyelination. But there is also loss in amplitude, which is conduction block. And then we look at the amplitude here. If it was a general axonal degeneration also, then this amplitude should be reduced, but it is not. In this case it is 6.1, and that is within normal limits. So this recording shows demyelination and conduction block and no axonal involvement. Here we have a similar situation, extensor digitorum muscle here, and recording from stimulating at the ankle, below knee, above knee, and you see the responses and the shapes of the responses. And here we get the abnormal response already at the stimulation below the knee. So the pathology must occur distal to the stimulation below the fibula head. So it's not across the fibula head. No extra changes occur when we stimulate above the fibula head. Here's another situation where we have abductor hallucis recording, and we stimulate at the ankle and at the knee, the tibial nerve, and you see at the distal stimulation we have a very pronounced dispersion of the signal and slowing of many components. And when we stimulate more proximally, we do not have more of that slowing. So all this slowing and all these changes occur very distally in this case of CIDP. Then a few words about sensory recordings. We can do them orthodromically or antidromically. The antidromic are less painful. We get larger amplitudes, but there is always a risk that we also get a muscle artifact in the different situations. And the orthodromic, there is no muscle artifact, and the lower amplitudes. We use the antidromic in one technique of carpal tunnel testing, the so-called 14-7 technique. We use it in sural nerve recordings and in radial nerve recordings. Orthodromic we use in some other situations, including some techniques for carpal tunnel. The conduction velocity is the same in both directions, and they have advantages and disadvantages for the different nerves. For the sensory recording, we can either use the fixed bar electrode or ring electrodes, or sometimes the sensory needle recordings. The start of the signal is either when it starts to leave the baseline, and that is very difficult to define often. So a better and more fixed position is the positive peak, or the place where the signal is turning upwards in negative direction. The negative peak and the positive peak. Latency is often measured to the positive peak or negative peak. The duration is measured between the two peaks here. Amplitude is measured between baseline and negative peak, or in our case with the computer will draw a line between the peaks like this and measure from that line just up to the negative peak. That takes care of problems if we don't have a good baseline. We can also measure the area under the signal between this line and the signal itself. Here is one very important aspect, and that has to do again with the recording from two electrodes that we always do. Here is a fixed bar electrode, and one field pad is here and one field pad is here, and the nerve is going under the electrode. The first field pad is recording this one and the second this one, and there is a little delay between them, which is the conduction time here. And what we record in our instruments is the difference, this minus this, like this. And you can imagine that if these electrodes and these signals are very close together, then we get very low amplitude, more or less zero. So the shape of the signal, amplitude, duration and everything depends on the travel time between them. That means it depends on the distance between the electrodes and also conduction velocity. And this is very important, particularly when we do the recording with ring electrodes. We must measure so that we get identical distance each time we do the recording in a patient, and also when we obtain reference values. Here we have a simulation where we have different distance between the ring electrodes. Here they are very close together, and then we separate them more and more, and we obtain a maximum amplitude at a certain distance. And then if we go at longer distances, then we start to see the effect of the other electrode. So this is now the electrode of the first ring, and here is an upside down of the second ring. So it is important to be aware of the sensory signal's dependence on the distance between the recording rings or field pads. Another well-known thing in sensory neurography is the effect of temperature. With this recording, this is an antidromic recording to digit 3. This is 31 degrees on the back of the hand, and here we have cooling 20 degrees, and that gives many effects. The amplitude is increased, the latency is also increased, and the total duration is increased. So that can be a problem in carpal tunnel study. We see long latencies, and long latency can be either carpal tunnel or a cold hand. Cold hand has typical high amplitude, and carpal tunnel have normal or low amplitude. So we measure the temperature on the back of the hand should be more than 29 for the hand and 27 for the foot. If it is less, then we heat with heating pads, or the patient has the hands in a water basin. The electrode position I will show in a handout that will be provided. It is not any principal difference in the thinking and interpretation when it comes to sensory recording compared to the motor recording. There is a difference in the way that we perform the study, since we do not need to subtract any distal problem as in motor, but the velocity is easier. It is simply to measure the time difference in responses between one stimulus position and the response. The differentiation between axonal and demyelination, it is the same principle, but some different figures for that, but the principle is the same with amplitude and velocity combination. And in the same way we define conduction block as the amplitude drop between two stimulation positions. So that is the end of this lecture, and I'm ready to take questions.